Okay, welcome to the second session of CFAIL. We have two talks. The first talk is from discrete log to lattices. Maybe the real lessons were our broken schemes along the way. And the presentation will be given by Alison and her co-authors.
Thank you. Just to set expectations for the logistics here as well, if you have questions as this goes along for the Q&A at the end, please put them into the chat in the IACR chat, where we'll be monitoring for questions. This talk is going to start with a pre-recorded video portion, and then we do have all the authors live to answer questions at the end, and then we'll pass it over to the other talk of this session, which will be done live here on Zoom. Just to set expectations for this talk in particular, this is not intended to be a survey of all of the incredible amount of wonderful work that is done in group and lattice-based cryptography. This is something much dumber than that. It is an exploration that we did going back to just the very basics of groups and lattices and looking for if there are any kind of missed opportunities for parallels or connections that could be used as pieces of fundamental strategies to generally move primitives back and forth across the lattice, across from the lattice world to the group world, etc. So we're not going to be showing you the best things that are known about lattice crypto or group crypto or anything like that, but we're going to show you our thought process in going through trying to build these bridges. And huge thanks to all my co-authors who helped me put together this video that I will play for you now.
Hello everyone, and welcome. I'm Eli. Most modern cryptographic primitives are designed based on one of two very different types of assumptions. In the first universe lie discrete group-based assumptions, such as discrete log and Diffie-Hellman. In the other universe are the more approximate lattice-based assumptions, although still technically discrete. The purpose of this project was to find a connection between these two distinct worlds, hence the title, From Discrete Log to Lattices. Maybe the real lessons were broken schemes along the way. First, I'll describe a little bit about both of these worlds, and how I began to build a very thin bridge, or perhaps more of a single stepping stone, between them. The simplest assumption in the group-based world is the discrete log assumption. This boils down to the idea that taking logarithms is hard. However, there are fast algorithms to approximate logarithms over the reals, and so instead, we look at some particular finite group. Since these algorithms work by exploiting the continuous nature of the reals, they are of little help here. There are very specific finite groups where people think that the discrete log problem is hard. For example, certain elliptic curve groups. However, for simplicity, we can think about this group as Z mod Q star. Formally, the challenge is, when given G, a group element, and G to the A for some number A, to calculate A. In the real numbers, this is exactly the typical logarithm. Intuitively, this is a very discrete problem. There is no margin for error and only one solution. In particular, we care about a slightly easier problem, the Decisional Diffie-Hellman assumption, or DDH. Given G, G to the A, and G to the B, one should find it impossible to even recognize G to the AB if one passed it on the street. One would think the easiest way to solve this problem is to first calculate A and B, and then multiply them normally to get AB. This immediately would give G to the AB. Thus, if one could solve the discrete log problem, one could easily solve DDH as well. The main takeaway from the DDH assumption is that multiplication in the exponent should be hard. These assumptions, along with other group-based problems, allow one to do basically all of cryptography. For our purposes, however, we will focus on key exchange. In key exchange, the goal is to get Alice and Bob to agree on some shared secret key over an insecure channel. At the end, they should share some secret information, but any listener should not be able to compute any information about it. In order to illustrate Diffie-Hellman key exchange, which is a particular instantiation of key exchange depending on the DDH assumption, please enjoy the following comic. Alice has here in her stomach a number A. She raises G to the power of A and tells Bob the result. Bob has in his stomach another number, B. He does the same thing, telling Alice G to the B. Now Alice can raise G to the B to the power of A, since she knows A, and calculates G to the AB, which he then stores as the shared secret key. Bob can raise G to the A to the power of B, since he knows B, to calculate G to the BA, which is the same as G to the AB. Now, Alice and Bob agree on the same secret key. Meanwhile, any listener only knows G to the A and G to the B, and so by the Diffie-Hellman assumption, wouldn't even recognize the secret key if they saw it. And so this is both a secure and correct key exchange scheme, depending on the DDH assumption. In the other side of the universe lives lattice-based cryptography, which, as the name implies, is cryptography based on lattice assumptions. Remember learning how to solve systems of linear equations in linear algebra? In general, that was pretty easy. However, with just a small margin of error thrown in, the problem becomes much, much harder. For the purpose of computability, we work over ZQ. We will define A to be a random m by n matrix, while S will be a column vector of length n, all over ZQ. Given both A and AS, it is very easy to calculate S using linear algebra. As an example, consider A and S as follows. The fairly complicated numbers, but you can see on the slide what the particular example is. To find S, all one needs to do is solve the system of linear equations where the coefficients are simply the coefficients of A, and the values on the right-hand side are the values of AS, which an attacker would know. As you can see, this is not very hard. I have the solution there, which I can find using very basic linear algebra techniques. However, what happens if you add in some random noise? Instead of getting A and AS, what if we sampled some small random vector epsilon and gave you A and AS plus epsilon? Is it as easy to calculate S? Probably not. Now, take a look at the same example, but with some noise added in. Epsilon is given here. We can similarly get a system of linear equations, but now they're approximate linear equations. Again, the coefficients are the coefficients of A, but the right-hand side is now the values of AS plus epsilon. And the goal is to find x, y, and z such that these equations approximately hold. However, solving these directly using linear algebra techniques will lead to no solution at all, since the system is overdetermined. And so therefore, the normal linear algebra techniques will not help at all. The learning with errors assumption states that when given only A, it is very hard to distinguish AS plus epsilon from a completely random vector. Most of what can be done in cryptography based on group-based assumptions can also be done based on LWE and lattice-based assumptions. Furthermore, since LWE is thought to be hard even for quantum computers, cryptography in the lattice world is often thought of as post-quantum cryptography. Therefore, we have two different, entirely separate ways of constructing the same cryptographic primitives. In order to begin building a bridge between these two worlds, we asked the very simple question: what is the easiest, the dumbest possible way to translate Diffie-Hellman key exchange into lattice world? Just as in Diffie-Hellman key exchange, we decided to, at first, have the secrets be random scalars. In Diffie-Hellman, the trick is that one can calculate G to the AB from G to the A and B, or from G to the A, B and A. Here, however, this same kind of multiplication doesn't quite work. If one has A plus epsilon and B, multiplying them gives AB plus epsilon B. While A plus epsilon is close to A, AB plus epsilon B is not close to AB, since multiplying some small noise by a large number will give a large number. For example, if epsilon is 2 and B is 1500, epsilon times B would be 3000, clearly also a fairly big number. Our solution was instead to give out approximate values of A multiplied by each power of 2 from 1 to log q. That is, if we choose m to be a vector of all the powers of 2, ma plus epsilon is the vector 2 to the I times A plus epsilon I for all I from 0 to log q, which we will denote as lambda. Now, if we write out B in base 2, we can create a 0, 1 vector B bar of length lambda. This operation, in some sense, undoes the expansion of MA, and in fact, B bar times MA simply gives back B times A. We can create A bar likewise, such that A bar times MB gives out A times B. Since A and B are scalars, these are equal. Since b bar is a 0, 1 vector of length log q, b bar times epsilon is also small. That is, the error will be multiplied by at most log q. And so if q is sufficiently small, then this multiplied error is also small. Thus, b bar times ma plus epsilon is fairly close to ab. At the same time, a bar times mb plus epsilon is fairly close to ab as well. This trick can be used to create the following Diffie-Hellman Ask Key Exchange, which I've illustrated in a new comic. Here, Alice and Bob again start with a and b, respectively, inside their stomachs. This time, instead of g to the a, Alice samples a small epsilon and publishes ma plus epsilon, which she will call a, capital A. Now, Bob similarly will publish capital B, which will be mb plus epsilon prime for some sampled epsilon prime. Now, since Alice knows a, she can calculate a bar, and thus Alice can multiply a bar by capital B to approximate ab. Similarly, Bob can multiply b bar by capital A to approximate ba, which is equal to ab. Thus, Alice and Bob share approximately the same secret, and so we have approximate correctness. So, are we done here? Is this the perfect equivalent to Diffie-Hellman in the lattice world?
That's a nice try, Eli, but unfortunately, no. Oh! In fact, it turns out that given all the information that Alice gives us, anyone, even an attacker, could determine the exact value of Alice's secret, A. Let's see how this would go. So, to summarize what Alice gives us, we're given approximations on A, on 2 times A, on 4 times A, all the way up to 2 to the lambda times A, which is the biggest power of 2 that is smaller than Q. And all of those approximations are up to an error of plus or minus big N, where here we'll only assume that big N is much smaller than Q. So what this means is that we have, for each of the of A times the power of 2, we have an interval of length about 2 times big N in which it lies in ZQ. And if we knew that not in ZQ but in the regular integer Z, so if we had an approximation, for example, of 2 to the lambda times A with an additive error of big N, then we could very easily get A by simply dividing both sides of the highlighted equation by 2 to the lambda, because when N is divided by 2 to the lambda, it becomes smaller than 1, and so we would just have to round this value alpha of lambda over 2 to the lambda. But division doesn't quite work the same way in ZQ. It's slightly more annoying, and let's see why. So I like to illustrate ZQ in a circle because it makes it clear that 0 is close to Q minus 1. So here we're working in, just imagine that we're working in Z13 and that we have an interval for 2A. So let's imagine that we know that 2 times A lies between 2 and 6 in Z13. What are the possible values that A could have? Well, some of the possible values are the one that are pretty intuitive to guess. If 2A is between 2 and 6, then A might be between 1 and 3. So we have possible values 1, 2, 3. But it turns out that there's some shadow value, another side of the circle in which A might lie. For example, if A is 8, then 2 times 8 is 16, which modulo 13 is 3, and that also lies between 2 and 6. So A might be either between 1 and 3 or between 8 and 9. And in general, dividing by 2 in this way will always divide an interval into 2 smaller intervals of roughly equal size that are on opposite sides of the circle. And that's not good because we really only know how to deal with intervals. And if we divide not by 2 but by a smaller factor, it gets even worse. For example, if we know that 4 times a is between 2 and 6, then it gives still as many values for a, but they are now spread into 4 parts of the circle. And in general, if we know a value for k times a, if we have an interval for k times a, then this gives k possible intervals for a spread all around the circle. So not only does it not decrease the number of possible values we have, it spreads them around, which makes it basically unusable. So how can we do anything with those multiples of a then? We have to remember that we don't only have one information, because in the attack that we had for values in the regular integers, we only used the biggest multiple. We only used the approximation we had on 2 to the lambda times a. But if we combine the information that we have on all the multiples, maybe we can corroborate this information in some way and get over this problem of dividing, which spreads the possible values around the circle. So let's try and do this. So we, from alpha 1, which is one number that Alice gives, we have an approximation of 2 times a. So we have an interval in which we know that 2 times a lies. And that's the circle on the very left. And from the division trick that we just saw, that means that a lies in one of the 2 smaller yellow intervals in the center circle. But we also know from another piece of information that Alice gives that a lies in the pink interval on the right. So it turns out that, yes, we can actually combine this information in a meaningful way. Because if we know that a must be in one of the 2 small yellow intervals on the left, and we also know that it has to be in the pink interval, then we know that it has to be in the leftmost of those 2 yellow intervals, because that's the only one that intersects, that overlaps with the pink interval. So that means that now we've really managed to go from an error of plus or minus big N to plus or minus big N over 2, because we've shrunk the interval by a factor of 2. So can we keep going? Can we go to big N over 4, big N over 8, etc.? Yes, we can do, but we have to start from higher, not just from 2a. We have to actually start from 2 to the lambda times a and go down progressively. Let's see how this goes. So in our case, with Z13, that would mean starting from alpha 3, which gives an approximation on 8a. So from this approximation of 8 times a, we can divide it by 2, which gives us 2 possible intervals for 4 times a, which are both twice as small. But we also know from alpha 2, we know that 4a has to lie in the pink interval on the bottom left. So that means that out of the 2 yellow intervals, the leftmost one is the one where 4a actually lies. And then once we have this smaller interval for 4a, we can repeat the process. And now we have 2 even smaller intervals for 2 times a. And from the interval that we know on 2 times a from alpha 1, we can figure out that it must be the rightmost of those 2 intervals. And then we can repeat the process again for a, where we finally get the exact value. So that's very cool, but also very sad, because that means that we don't have a key exchange scheme anymore. But this technique really uses the fact that the multiples that we have, the approximations that we have on multiples of a, the coefficients are powers of 2. And we use that in the fact that when we go from 2 to the lambda minus 1, we only have to divide by 2, which splits the bigger interval into two smaller intervals. But if they were more than a factor of 2 away, we would have to divide by a bigger factor, and that would divide this interval into many tiny pieces, and we wouldn't be able to easily recognize which one of the intervals is the correct one anymore. So does that mean that if we just change the coefficients to be, let's say, random integers and make sure that there's no easy relationship between them, there's no small factor, not small if a small factor away, then problem solved?
Are we safe, Victor? Are non-powers of 2 safe? Is our scheme now secure? Of course it's not. This is CFAIL. It's busted. But it's busted in a slightly different way than it was before. So the first thing I'm going to ask is that, what if we consider a more general framework? So instead of giving approximate values for 2 to the I times A for all I, Alice is instead going to give approximate values for C sub I times A for arbitrary coefficients C1 up to Cm, and these are all in Z mod Q. And they're going to be decided in advance and publicly known, yada yada. The errors are still going to be assumed on these approximations to be distributed on the interval of -n up to n. But note that the m here doesn't necessarily have to be close to log of q. So that's Alice's side. On Bob's side of this generalization, we still are going to use the same oracle trick for legitimate computation of the key. So we're going to assume that there's an oracle that, when given a b, returns m integer weights, w1 up to wm. But this oracle is going to have 2 guarantees on it, 2 conditions. First, for correctness, we're going to say that the sum of all the wi's times their respective ci's is equal to b. And then secondly, we're going to say that the sum of the absolute value of all the weights is going to be less than a big W. Now, the second part is just to ensure that when we compute AB from the CI's times the WI's, that this estimate is going to be bounded by W times N. If the weights were too big, i.e. bigger than this, they would amplify the errors in the approximations that Alice gave in the first place, and the error we would get on AB would not be small anymore, and so it wouldn't be usable. Now, with this generalized framework, what does the actual attack look like? Well, to lay it all out, it's going to be the same interval style attack as before, but assume we currently know intervals of length less than or equal to L for all of the CIAs, and we want to find an interval of length L over 2. And we want to find this because that, as shown before, is going to let us find a specific C sub k times A. Now, to do this, we're going to call the oracle on a particular value of B, in this case 2 times W times C sub k, and then we're going to compute an estimate for B times A using the weights that the oracle returns. And then once we have that, because of the guarantee on the oracle, we know that the interval for the range of possibilities for our estimate AB is going to be of length at most L times W. Now, by dividing this interval by 2W, we're going to find an interval of size L over 2 for our particular C sub k times A that we wanted in the first place. I know that sounds a little abstract and hard to visualize, so we're gonna take a look at how this division works using the very nice circle diagrams that Victor made. So how does the division by 2w work? Well, generally, let's assume that we know k times x is in some interval L to R for a small integer k. What can we say about x? Well, in the case before, for k equals 2, we saw that the values of x were in two opposite intervals on the circle representing z mod q. Now, in general, the possible values for x are going to lie in k different intervals that are all evenly spread around z mod q. To be a bit more precise, if k times x lies in the interval L to R, then x lies in one of the k intervals L plus I times q over k to R plus IQ divided by k. And then this is going to be for some I between 0 and k minus 1. And all of our division and rounding are going to be performed in Q. Now, in our case, for this generalization, we have an interval of length LW for 2 times W times CKA. So when we divide by 2W, that's going to give us 2W possible intervals of length at most the floor of L over 2 for the CKA we're looking for. Okay, so we know now that CKA is going to be in one of 2W intervals that all have the length we're looking for, evenly distributed on the circle. Now, just like the first attack that Victor outlined, we will use the interval of length L that we already know to determine which one of the 2W intervals is the right one, right? Just which one overlaps, and the one that overlaps is the right one. Now, in order to get this overlapping properly, we have L equal to 2n initially, and this is so everything is spaced out enough such that we can determine the correct interval uniquely. Now, using the same expression as before, this means that we need the 2W intervals to be spaced out by more than 2 times n. So that means we need 2W times 3n plus 1 to be less than or equal to q. I want to say this is a reasonable assumption, right? Since the error that Alice and Bob have can be as large as n times w. And the interval in which a successful value of AB lies is going to be of size 2 times n times w. So if we had a smaller q, the attacker would have a pretty significant, like 1/3 probability that they would get the key right just by randomly guessing the element. And that's not great from a security standpoint at all. So with this procedure that I've outlined, we are able to find a particular CK times A. Now, if we do this for all K, we're going to go from intervals of size 2n to intervals of size at most n, right? And then, since the precision we get in this procedure of looking at overlapping intervals gets more precise as the interval sizes get smaller, we just do this again on all k, and we get intervals of size, n over 2. Do it again, and the intervals of size n over 4, etc., etc., etc. Now, we do this, log n times, and we're of interval size 1 and the answer is precise, and so we've obtained a precise answer for all of the CKAs. And then all of these coefficients were publicly known beforehand, so we can recover A completely just by computing C1 times A times C1 inverse, right? And we know which one is, and we know which C is the right one. So everything is still broken, and it's efficiently broken too. The runtime of this whole procedure is O of M operations for a single division step, and we have to do M log n of these steps. So the total runtime of the attack is going to be O of M squared times log n operations. So not good. But is all hope lost still? Is there a further generalization we could do? What if we just got rid of the oracle? i.e. we cheat. Well, if we cheat like this, we lose all the functionality we wanted. But maybe we have some security?
Garrison, we haven't failed just yet. That doesn't come until later. Just zoom out. The answer is right in front of you. If neither Alice or Bob, nor any adversary has such an oracle, our challenge starts to look very familiar. We have M equations, where the Ci's, B's, the B, and the epsilon i's are all scalars. So pictorially, we can look at it like this, where we have M-dimensional vector C and epsilon, and we have scalar B, and we compute C times B, it's a scalar product there, plus epsilon. And this is indeed LWE with n equals 1, which we know is hard if Q is exponentially large. So we have a good problem here, a standard assumption upon which we can base our key exchange. But the question is, how do we harness this structure? The answer is, when we fail, we cheat. Given the CI, Alice and Bob can first randomly choose small wi that sum to their secret values A and B. This is instead of first choosing secret values A and B and then trying to find small wi such that the sum of wi ci sums to A or B, which we know would enable us to have an attack. So in essence, the real secrets are now the wi's. But we know from the leftover hash lemma that A and B are still epsilon close statistically to uniform. So now we go over our first exchange. That's based on LWE with n equals 1. So here are Alice and Bob. They have a shared public vector C that's m-dimensional over ZQ. So what Alice first does is she chooses her small binary vector WA, which is m-dimensional, and also an m-dimensional noise vector epsilon A. Then, using this, she computes her secret A, which is a scalar in ZQ, by computing C.WA. From here, she then calculates her value to be published, big A, which is, as before, CA plus epsilon A, and it's a vector, an m-dimensional vector over ZQ. Then Bob does the same, and Alice and Bob exchange big A and big B publicly. So then, given big B, Alice simply computes WA.B. And so if we split this up, remember B is equal to this CB plus epsilon B. So when we calculate WA dot C times B, this part will just change into A times B. And then this part over here is just small noise vector epsilon B dotted with this small binary vector, so the noise won't blow up too much. And so Alice gets around AB. And Bob does the same, so he gets around B times A. Okay, so now how do we extend this to general n? In fact, it's sort of easy. We can extend the CIs and thus A and B to n-dimensional vectors, and our key exchange will then be based on LWE with general n. So what we do is we now choose small vectors, WA and WB, such that this new secret vector A, which is n-dimensional, is equal to the linear combination of the CIs weighted by the components of WA. So before, we had this m-dimensional vector C made up of scalars Ci, and we dotted it with this m-dimensional binary vector WA to get our secret scalar small a. And then our public big A, which is m-dimensional 2, was calculated by this Ca plus epsilon a with our little scalar a. But now we're saying, okay, A is n-dimensional, and we compute little a by this multiplication of C times WA, where C now is still size m along this dimension, but here we have expanded it to be n-dimensional. So each CI is an n-dimensional vector. And so here we still get big A that's an m-dimensional vector, but instead we compute it with big C transpose times our secret little a plus the noise epsilon a. And note, when Bob comes with his WB vector, if we look over here, we originally calculated WB dot C, which would turn into B times A. And here we're doing the same. We're just computing WB, multiplying C transpose on the left by it, which will give us the vector B, m-dimensional, and so we get B dot A. And so really all we done is blown up our dimension to general n. So now we have this general exchange. So C is now an n by m dimensional matrix over ZQ. Alice first does what she did before, simply calculate this m-dimensional binary vector and this m-dimensional noise vector. And we just make the changes that I discussed on the last slide. Notably, we calculate little a as an n-dimensional vector over ZQ by multiplying the matrix C by WA. And then we compute big A, which is the public value, as C transpose A plus epsilon A. And Bob does the same. Alice and Bob exchange big A and big B publicly. And so now, given big B, like I said before, Alice just calculates again WA times B. So the first term is WA times C transpose times B. This part will, of course, turn into A transpose. So we simply have A dot B here. And still, this is just an m-dimensional noise vector dotted with a binary m-dimensional vector here. So again, our noise won't blow up too much. And Bob will do the same thing symmetrically and get B dot A, about B dot A. And so Alice and Bob will approximately agree on the same value. And if you want to be fancy, you can do some error correcting to make sure that they round to the right value. But really, you can just do rounding to Q over 4 or through Q over 4 and interpret that as a 0 or 1, and that's good enough. So what else can we do? Can we do anything more than two-party Nike? Well, first thing is three-party Nike. In the discrete log group world, this requires a bilinear map, of course. So it would be quite difficult to extend this to the lattice world. One could also do an adaptively secure IBE, perhaps based on the dual system paradigm. Again, this also requires bilinear maps in the group world, so this also poses quite the challenge for us. And there's a number of other things that one might imagine they could build with lattices that already have constructions based on group assumptions. But in short, we failed to do any of this. Oh! So, you know, that's the story of our work.
Thank you. So I'm now looking at the chat window. Some people were saying that they had a recording that was in low resolution, or that there was a time lag. So everything on my end is fine. So I guess people watching it again on YouTube will have a full resolution video. So I am looking at the chat window again to see if there are any questions on the talk. I don't see anybody asking any questions. So yeah, I guess I'll ask a question myself, but I'll be more general then. So I see a bit of a relation here. If you're talking about adding noise to your computation and somehow then filtering out that noise, to perhaps constructions where you're trying to add some side channel resistance, because an attacker might want to do some measurements and do computations. So a question to all of you is if perhaps some of the earlier things in the presentation are a bit related to that. If there are any connections between the fields.
Yeah, that's a good question. I'm sure that there probably are connections between these things and a lot of other fields that we're not aware of and that we didn't really look into. One additional related connection that I think comes to mind for people kind of right away is also the connection to fully homomorphic encryption style techniques that also sort of deal with this problem of like, okay, I'm going to have something small times something big, and how does the noise not blow up? And so we're definitely bordering on like a question that seems to crop up in a lot of other places. And we haven't yet found ways to sort of take insights from those other solutions and make them relevant to the sort of core problem that we're working on here. In the case of fully homomorphic encryption in particular, for instance, that mechanism of sort of using the bit decomposition is very much kind of what we were trying to do here, and one thing that was inspiring us in trying to use the powers too. But it doesn't work in this case because in fully homomorphic encryption, you have this secret key which is allowed to be like precise in its action, and that's where like the powers of 2 blow up happens, and you don't have this like symmetry between objects that you have here, that like you have 2 things that are multiplied and they're kind of at even footing. It's not like you can sort of push things from the ciphertext into the secret key that in some way you're doing in the fully homomorphic setting. So as a general non-satisfying answer to your question, I'd say like I'm sure that there are relevant insights from other fields to this problem because it's just so close to so many other problems, but we haven't yet found a way to like leverage any of those.
Yeah, thank you. I see a question now on the chat from Tanya Lange, who is admitting that she has not read the paper. She failed to read the paper, but she would like to know if it is possible to verify if the keys are valid.
I don't think so, or at least that's not something we checked, or I guess there are two things that I think that question could be asking about. One is how do you tell like that the shared key, right, is ultimately the right sort of rounding, since you're getting two different approximations of it on different sides. And that, I think, yeah, we were just relying on sort of assuming that one could set the parameters such that the probability of it not being right was vanishingly small enough that we weren't concerned about that. Yeah, so we don't provide a procedure for verifying that.
Mm-hmm. Question just came in from Rohit Chatterjee. I guess it's a question mostly about the title that says from discrete log to lattices. So can you maybe comment a bit further on the link between those two settings?
Yeah, which is basically, you know, where the core failure is. I'll give you a little bit of the backstory of sort of what obsesses me about this problem. So in particular, I spent a lot of my PhD sort of working on dual system proof techniques in the group domain and bilinear groups, and they rest upon this sort of structure of a subgroup that exists inside bilinear groups. And it's kind of in and of itself like a relatively basic group type structure. And you might hope to kind of just find, you know, other instantiations of that structure sort of inside other algebraic domains, like very much so, like lattices, or and this is a similar inspiration, I think, to the building of multilinear maps, which is trying to replicate even further structures. But before we get to multilinearity, there's a somewhat smaller, more constrained sort of structure inside bilinear maps of these kind of subgroups that enable these kind of adaptive proof techniques. And I've spent a lot of time trying to figure out how to simulate those structures in lattices, and trying in a lot of very particular ways and failing in a lot of very particular ways, and sort of then stepping back and saying, you know, this really is a lot of sort of detail on top of a fundamental question, which is just, you know, the basic mechanism for hiding secrets in groups is to put them in the exponent. And subgroups are no exception. It's just like you get a little fancier with what sort of things you can encode in the exponent. But fundamentally, you're hiding things by putting them in the exponent. And then the operations that you can allow on sort of those quote unquote encrypted secrets is the things that you can efficiently do sort of in the exponent. That's why bilinearity gives you a somewhat homomorphic kind of extension of capability, because it allows you to do sort of one multiplication in the exponent without just breaking the D-log problem and making the exponent sort of visible. And in lattices, you have this sort of similar in spirit mechanism that the way to hide something is to add noise to it. And then the operations that you can do are the things that you can do sort of on top of noise without noise blowing up. And I'm very much obsessed with like, what's the right transformation between those two strategies of hiding information, and in parallel between those two ways of operating on hidden information. And if we could build a bridge very fundamentally between putting things in the exponent and between adding noise, then we wouldn't have to write all these like 100 papers of here's this thing in lattices, here's this thing in bilinear groups, here's this thing in groups, here's this thing in lattices. We could have an actual sort of procedure for saying, I can turn the crank and take a lattice scheme and make it a group scheme, or vice versa, which is very much not what we did in this paper because we don't know how to do it. But that's why we're spending a lot of time with just this basic algebra of hiding things by noise and hiding things in the exponent, and trying to really understand to what extent and why are those strategies different, and are their algebraic capabilities in the end really distinct, or is there some kind of like homomorphism sort of between them? And so that's the question that motivates the work, although, you know, the answer as to what is that transformation is very much an open question.
That's very interesting. I see that Tanya has now clarified her question a bit. It gets technical, so I'll just read it and then I'll see if it's maybe a good thing to either answer it now or take it offline. So she's asking regarding her question about whether you can verify that the keys are valid. She's thinking about reaction attacks that send somewhat invalid shares to extract the secret of the other party. So this is, of course, assuming that the keys are reused, which is what you would want in Nike.
Right. Yeah, honestly, I haven't thought about it because, you know, we were not sort of interested in this as a Nike scheme. This was just sort of like a proof of concept. We were trying to think, well, if whatever connection we're trying to build can't even do this basic like one-use Nike, then obviously it's not going to extend to like dual system IBE. So this was kind of just like our testing ground, and it does, you know, we did prove that it works as a one-use Nike, but yeah, we didn't go further than that and try to verify these other properties.
Maybe that's a paper for next year's CFAIL.
Or something, or they could succeed. I mean, I don't know if it's hard. It might not be hard, or it might not be true. Yeah, anything on that is possible.
Mm-hmm. Okay, I think we still have time for one or two more questions. I see a question coming in from Daniele Micancio saying, so based on all we know and understand at this point in time, would you describe the lattice schemes as, number one, loosely inspired by bilinear map schemes, but genuinely different? Or number two, simple adaptations of bilinear schemes to lattices?
I'm not sure. I'm not sure that those things are so distinct. I think they're in some sense kind of both. I think if you stare, for instance, at Bonet-Boyan bilinear IBE, and you stare at Agarwal-Bonet-Boyan lattice IBE, which there's no coincidence, of course, that some of the researchers are the same, you'll be pretty convinced that, you know, they took the bilinear thing, they wrote it down in lattices, and but it doesn't work sort of by coincidence. Like there are sort of like careful decisions that have to be made in the lattice realm to like make that work. Because as we see, like whenever we try to make that into an abstraction, like if you try to imagine that whatever was sort of done to make Bonet-Boyan into Agarwal-Bonet-Boyan, and you try to write it as a kind of general purpose machine that's kind of like take a group scheme and turn out a lattice scheme, like it does not work like in general. So like at the same time, it is a simple adaptation, and at the same time, there is something different or coincidental or, you know, magic about that particular one works. And so, and of course, there's been, you know, huge success in building lattice schemes that are definitely, you know, have nothing to do with bilinear schemes. For instance, we have no bilinear Foliomorphic encryption and vice versa. But yeah, I think for many of the cases where the bilinear schemes preceded the lattice schemes, you can trace the inspiration and you can see it. But I think the times that it happened to be simple or seems simple in retrospect are perhaps more misleading than I had initially hoped. So I guess I reject, in short, I reject the classification, which is perhaps not a helpful response.
It has to be number one or number two, the way the question is phrased.
Damn. Failed to answer the question.
I see another question coming in from Habin Chang, saying if trying to differentiate lock and lattice problems, would you consider comparing the computational complexity classes of the problems?
That's an interesting question. Personally, I don't care. I don't find it interesting. Like, I think it's an interesting mathematical complexity theory question. I'm not at all drawn to it because it just makes my job as like a builder of systems like harder. Like I'll take anything. Like I'll take any assumption that isn't known to be broken. And so I think we might gain insights from looking at that. But I've been approaching this personally much more as a construction of scheme problem. And I guess it's not clear to me how a study of the computational complexity classes would really guide me in that. But that's also just a personal bias that I find computational complexity classes beyond just, you know, the basic sort of hardness to be super intimidating and annoying to work with.
Mm-hmm. Okay. I guess Daniel Mikanchu is clarifying that it is an inclusive or for the 2 points in the question.
Great, thank you. Thank you for, you know, retroactively making my response acceptable. I appreciate that.
Yeah. Okay. I guess then, thank you, Allison, for a really interesting talk and conversation, and also to your co-authors. Now we have another talk, the last talk of this session, by Martin Strand, titled, "Can There Be Efficient and Natural FHE Schemes?" Martin, the floor is yours.
Thank you, Nikki. See if I get this right. That should be right, isn't it?
Yeah, that looks very good.
Brilliant.
The first slide, at least.
Yeah. Let's put the bar there, shan't we? Right. So the question is, can there be efficient and natural FHE schemes? And that's, I realize, closely related to the talk we just heard from Alison and, well, rather from her co-authors. So when we look at El-Gamal, Diffie-Hellman, and schemes like that, it all feels very natural, at least to me. Things are exact, they work out, we have equations, and at the end we have something very nice popping out. I like that. And the question is, can we get some FHE scheme that does the same thing? So when most people think of FHE today, they think of the 2009 breakthrough by Gentry, which is noise-based. But that's not really the starting point. The starting point was by R.A.N.D. in 1978, and they asked two questions. Does this approach have enough utility to make it worthwhile in practice? Which I think we're still trying to find out. But, well, there have been some nice results in that direction. And then, for what algebraic systems does a useful privacy homomorphism exist? And I would claim that that question has gone mostly unanswered since 1978. There have been some negative results, but really what Gentry did was saying that, okay, this is hard, let me find a different way. So the timeline is, well, it started all in 1977 with RSA, and as we all know, textbook RSA is homomorphic multiplicatively. And then you have this privacy homomorphism the year after. And then we have El-Gamal, which can be either additively or multiplicatively homomorphic, depending on how you do it. Then a couple of years later, Ahituv, I'm unsure about how his name should be pronounced. Please correct me afterwards. Said that, okay, at least on vector spaces over the binary field, there can't be any of this. Then we have many years later Gentry, and then we have some years after that, and when this work was mostly done, there was a trend of posting noise-free homomorphic schemes on ePrint. And this is trying to rule out these in some sense. And noise-free schemes would definitely be natural in the way I hinted at in the beginning, in that you have exact equations and things work out, and you have some algebraic operations just working. As we all know, that's not the schemes that are being used or being experimented with when it comes to FHE. We're all doing noisy stuff, and we're doing even now we're doing approximate computations, and we're getting a lot better results by doing that. So let's have a look at bootstrapping. What's triggering this work? So if C is the ciphertext space, well then, under a normal full or somewhat homomorphic scheme, C is not closed under addition or multiplication, in the sense that if you multiply too many times, or even if you just add too many times, well, eventually you are going to get something that is no longer a valid ciphertext. And that's a problem. So therefore, we can do bootstrapping instead. Bootstrapping says that, well, if I can just do one operation and then apply some other operation to my ciphertext, I can get it back to square one, and I can keep on doing operations for as long as I want. And then it will be closed in C, but it will be on the expense of ciphertext size, computing time, and also it will totally ruin the distributive property of multiplication and addition. So bootstrapping is sort of solving this problem, but not in a nice way that I would like to have. So can we do any better? Well, the dream theorem would be saying that, okay, let this curly S be a collection of some algebraic structures S with two operations. So mathematicians are allowed to think categories now. And this S, this set is closed under both of these operations, and this second operation is distributive over the first one. Then we want a theorem saying either there are no practical FHE schemes that involves this algebraic structure, or something that says, well, actually there is. And it would be a dream to be able to prove this theorem, at least for the interesting cases. So let's try to draw a map of all of algebra. So to make algebra interesting, you need operations. You can have one operation like groups, or you could have two or more operations. Now I'm going to join those last two, because if you have more than two operations, well, then you have two operations. And I only care about two operations, at least for the purpose of this talk. So if we look at only one operation, well, then we have nice fully homomorphic schemes, with fully now meaning that you can do, well, you can use the operation that is available as many times as you want. So in this respect, El-Gamal is a fully homomorphic scheme. Whereas if you have more than one operation, you have fields, you have rings, you have vector spaces, you have modules, you have algebras, and so on. Can you have any fully homomorphic schemes over any of those? Let's see. Well, so what is a fully homomorphic scheme? To put it mathematically, I want to say that, okay, we have some plaintext space, we have some ciphertext space, and I'm defining two mappings, two maps, one epsilon that goes from the plaintext space to the ciphertext space, and some delta that goes from the ciphertext space to the plaintext space, in such a way that if you first apply epsilon and then you apply delta, well, then you have just used the identity operation on the plaintext space, which is what we recognize as being correct. Now, for it to be homomorphic as well, I say that, okay, if I have two ciphertexts in the ciphertext space, then I apply some operation in the ciphertext space and then decrypt, well, then I should be getting the same thing as first decrypting those two ciphertexts and then applying some corresponding operation in the plaintext space. And I think this is the right way to put it. The idea of homomorphic encryption is often written as saying the encryption of A plus B should be the same as the encryption of A plus the encryption of B. And it absolutely shouldn't. It's the decryption of something that should be homomorphic. But you don't want encryption necessarily to be homomorphic, because in encryption, you don't want it to be a function. You want it to be some randomized algorithm. So you want the randomness to do its part. Anyway, so what we're able to say is that, okay, if we have some homomorphic scheme that looks like what I just showed you, and I can prove that if you have some fully homomorphic encryption scheme that is also infinity hop, which is a term that was coined very early, which means that, well, fully homomorphic means that you can apply any circuit to your ciphertexts, and infinity hop means that you can apply as many circuits as you wish after each other. Well, if you have that, well, then I can prove that encryption is essentially always just applying this epsilon map that takes a message into the ciphertext space and then adding a random encryption of 0. And then I used so I'm selecting something from the pre-image of 0. So anything that would be taken to 0 by the delta map is fair game. And then intuitively, for this scheme to be secure, either this epsilon map or removing this randomness must be hard. And when I say plus here, that just means some operation which has an inverse. That is all I require from this plus. And that is what we typically expect from the plus. So I just put a plus there. Now, another theorem in this line of reasoning is that if you have some asymmetric FHE scheme, then it is secure if and only if it is hard to distinguish encryption of 0 from a random encryption. And that is more useful than it looks like, because that makes it very easy to just analyze some schemes very quickly. So I mentioned in 2015 there were some noise-free schemes posted on ePrint, and they had some very nice arguments about why this should be secure and so on and so forth. And I just looked at them, applied what is essentially a transformation that arises in this proof. And then I could very easily say that, well, these are not secure because I can distinguish encryptions of 0. I'm happy. And then some tried, well, let's put it in the quaternions because they're non-commutative and everything works fine there. Well, the quaternions can be represented as matrices over some field, and then I don't care about the quaternions anymore. I'll just go down to that base field and work with larger parameters, and I can break it. So it's looking pretty bad, and it's getting worse. So already in 1987, by Aituv, it was proven that there are no secure schemes between two vector fields over the same field. Well, that is ruling one whole category out. And if both P and C are fields, well, then we have no secure schemes between them. And that is partly from seeing that, well, then they must have some common base fields, then you can apply vector space logic on them, and partly by an algorithm by Lenstra, which is computable in polynomial time. So, okay, we can't use fields. And that is by itself nice to know, because we really want to do our computations in fields, because that's where everything works very nice. So let's look at some more partial results. So if R is a commutative ring with no non-zero nilpotent elements, so no elements that are suddenly going to zero if you add them or multiply them with themselves sufficiently many times, well, then we know that we can decompose this thing, and it will decompose into many fields. Each of these fields will have some extension degree over some base field, and then you will have a number of automorphisms over it. And counting automorphisms is really the right way of looking at this, I think. So if you look at El-Gamal or RSA, you will see that, well, allowable keys or valid keys are just automorphisms on the group that you define this thing on. So looking at automorphisms is a very natural thing to do. So if you have these rings that are, well, they're still quite nice, you could do some interesting computations with them. Well, then you see that this n must be large for there to be enough keys. And if this n is large, well, then you will have an awfully big ring. So it might not be very efficient. Very natural, but not efficient. So just how can I count this? Well, we have the Wedderburn-Artin theorem that says that you have this decomposition, and the Wedderburn-Artin theorem says that, well, you can decompose into matrix ring over division fields. But since we say commutative, well, then you have fields, and also said no nilpotent elements, then we rule out the matrices, so then we just have the fields. So this is really what the ring looks like. So you have different base fields, perhaps, and you have different copies and different expansions. And then you can just build this number from counting all of these. Right, so you can look at other even more exotic algebraic structures. If you take some semi-simple K-algebras, they're still pretty well behaved. You still get many of the same algorithms, so you can't have FHE over those. And in the general case over rings, the theorem I had up says that, well, the scheme can be secure if you can't distinguish a certain ideal from the rest of the ring. So far, we can do it with groups. We can't do it with fields. We can't do it with vector spaces. There might be some hope with rings and algebras, but they won't be the most useful rings and algebras to do the computations in. So you might not be able to do the computations you want to do anyway. And the keys might have to be very large. And then there's a question of modules. And if you don't know what a module is to a ring what a vector space is to a field in some sense. There's a lot more of nuance going on in modules, which could make them a handy hiding place for homomorphic schemes. So you have scalar multiplication, and you have addition, and you have multiplication coming from the ring. So that you could do something useful there. And then we have some positive result as well, because every abelian group is a module over the ring of integers. And we know that there are secure schemes that are based on abelian groups, which is looking good. And then we can have a closer look at, say, El-Gamal or Diffie-Hellman or any of the discrete log-based schemes. And essentially, it's only using multiplication in the underlying ring. So yeah, that's fine. If you look at the index calculus algorithm, which is the best attack we have currently, that is really abusing notation, addition, I'm sorry, abusing addition in the ring of integers to break the scheme that is based on this abelian group, which sort of explains why elliptic curves can be so much cheaper than Elgamal or Diffie-Hellman over just integers, because when using elliptic curves, you do not get easy access to the underlying structure from the integers. So even though we now actually have an example, it's a bit of a trivial example, and it seems that having this extra ring structure is possibly enabling some attacks, even if the ring structure is superfluous. So what are the failures here? Well, if you're working with FHE already, nothing that I said so far would be surprising to you. I suppose that's a bit of a failure. And we're not able to complete that dream theorem that is really classifying or characterizing where we could have natural FHE schemes. So we're not saying anything nobody knew, and we're not able to prove it. Well, on the other hand, we are actually writing it down. And I don't think anyone had written this down before we did. And I also think that these results sort of state that, well, looking in the directions we do with the noise, with all this approximate computation going on, is in fact the right direction. There's probably not much to be found with the more classical solutions. And if someone comes up with another candidate for a noise-free FHE scheme, apply the transformation that arises in this paper to it, and you will be able to break it very quickly, probably. So I think I'll stop there. Thank you very much. And Alison, thank you for nodding along the way. It was really useful.
Great. Yep.
There's a question from Daniele coming in on the chat, asking to clarify whether negative results are only for deterministic encryption schemes, or if they apply to standard probabilistic encryption as well. Well,
I would argue that they apply to probabilistic as well, because these mappings epsilon delta these are really models for these deterministic schemes, right? And then I say that, well, okay, I can let the C be a lot larger than P, and then we get some randomness coming in here. But you can still find a copy of the plaintext space within the ciphertext space. And with that copy being there, you could, with most of these, well, actually that's the whole point of this argument, is to identify this copy of the plaintext field, plaintext space inside the ciphertext space and build a basis for it from that. There are some more details in the manuscript, but I didn't want to get too technical. I think I was already pushing that.
Okay. I'm checking now if we have any other questions coming in.
I have a question in the meantime. I'm wondering what all of this has to say about the very related problem, it seems to me at least, of noiseless multilinear maps.
Oh, good question. I haven't looked at those for a while. Intuitively, I wouldn't be very optimistic, since multilinear maps imply a lot of other things. And these arguments don't really care about all those other things. So as long as there is no noise involved, and you say that I have something with no noise, and it implies, for instance, homomorphic encryption, well, if that would imply noiseless homomorphic encryption, I wouldn't be too optimistic.
I guess it seems to me, at least maybe the level of multilinearity behaves sort of strangely, because we would imagine, right, that we can't rule out bilinear because we think we have those. So it would sort of be a question of like, where is that sort of phase transition, which seems a little less natural for it to be like some particular value beyond which you can't go. But yeah, I share your skepticism for sure. It's just I can't wrap my head around two being special.
So if I remember, if I remember correctly, the way the first multilinear maps were created was by emulating graded rings, which is an exact structure by all means, and then replacing the indeterminate that is used as a counter, so to speak, or to grade the ring with some random element, and then just pretend that we still have an indeterminate, and this is a well-defined graded ring. So I think it's a very neat trick, but I don't see how you can do without it.
Okay, a question that I have. A question comes in from Habin Cheng, saying you mentioned that algebraic structures with more than two operations are equivalent to those with exactly two operations. Did I hear that correctly is the question?
Well, the point is there that I only care about using two operations in my analysis, at least for the purpose of this talk. And if you have more than two operations, well, you could pretend you only had two operations and then just use the other ones, the other operations as extra fuel for your attacks.
Mm-hmm.
Also, would tropical geometry be an option for a more exotic structure? By tropical, you mean where plus is replaced by, well, the standard plus is replaced by max and multiplication by standard addition. Is that right? Yes. I don't remember the properties there, but I wouldn't be very surprised if that failed as well. At least, so the whole point here is that I assume very little, or we assume very little from the various algebraic operations, and we didn't really assume that we had plus. We just assumed that we had something that would have an inverse, and as long as you had something with an inverse, we could make a lot of this fly.
Okay, I had...
Yes, please.
While other questions might still be coming in, I had a bit more of a philosophical question. So as you explained, this is something you worked on about 5 years ago, then put a paper on ePrint. What was your motivation to revisit this result?
I think there was the very existence of CFAIL. And of course, being a bit frustrated that, well, I got some reasonably nice feedback on it on Crypto 2016, and sort of got the impression from the reviews that it was within the acceptable boundary, but there wasn't enough room for it. There weren't any nasty reviews, at least. And then things went downhill from there, and also, of course, Nico, we had a bit of an email conversation about this paper, and you said that, well, the topic was interesting, but the paper wasn't well enough written to be acceptable.
Well, it wasn't failing enough. So,
and I can definitely accept that. I'm not going to say that there are so many reviewer two out there that it doesn't have. Also, of course, this paper was lying around at some journal desk for about 1.5 years, if not more. So it was kind of dormant. But what I want to say also is that if anyone has read it, either as reviewer or in any other capacity, and have useful constructive tips for how it could present its result better, I'm very, very happy to take those, because I think there's something of merit there.
Yeah, so I just wanted to clarify here, because CFAIL is a bit of a different conference from most other conferences. Whenever people submitted papers that seemed too much oriented towards a general cryptography conference and not describing the failure enough, then we had to make a comment about this to make sure that all the papers stay on track somehow.
Very good. I see also Daniela has another question.
Exactly.
It's a very good question. In what sense schemes with lightweight bootstrapping like Few and TFHE or Taurus FHE do not satisfy my definition? That is a very good question, because I must admit I haven't looked at the details of those recently, and this work was done before they came along. But I definitely think I will be looking at it. But I have a sneaking suspicion that there might be something about the laws of algebra not being necessarily completely satisfied. There might be something in there. But it could be interesting to see what sort of algebra you actually get from these schemes. Good question, Daniele.
Great. So I see one more question coming in. Maybe I'll quickly read it and you can have like a 1-minute answer. One more clarifying question. Your point was that the addition just required an inverse to fit in with your presented material. Doesn't the min-max operation in tropical geometry not allow an inverse, make it a semi-ring?
Oh, great, absolutely. That's a great question. And the answer is that we're not discriminating. So I use the plus because it's easy to assume things from the plus. But what I really say is that, well, we just want some operation with an inverse. So I'm very happy to take the multiplication in the tropical geometry and use that as my operation in that particular respect.
Okay, Habin says thank you. I see in the chat, Daniele says thank you as well. I would like to thank you on behalf of all of the participants. So this is ending the second session. In half an hour, we'll start again, and we'll have an invited talk by Stephen Bellofin, where he will talk about the evolution of IPsec.